everybody. I'm Ram. I work for IBM for the Linux Technology Center. I'm leading the what we call as the Ultravisor project, which is basically a secure virtual machine enabling technology. We had quite an exciting week this week. We had quite an exciting week. We booted our first secure virtual machine on Power 9 hardware in the lab, and that was quite a significant, quite an exciting event for us. So I know most of you will be asking what secure virtual machines is, and this talk is about that. So secure virtual machines, this is roughly my agenda. I'll be briefly stating the problem statement and then go through the technology pieces that make up the secure virtual machine. So what's the problem? The problem is not everybody wants to get onto the cloud because they are not very sure about the security of the virtual machine. Anyone can attack. There are bugs in the operating system, bugs in the hypervisor. Anybody can exploit it. Even if everything is good, you may not be able to trust the administrator. So how do we try to avoid this? Give those assurances, guarantees to workloads like healthcare, banking, government, that if you are running on these machines, on these secure virtual machines, your data will not be compromised or nobody will be able to steal your data. So how do we solve that problem? And the solution to that problem is make sure that the operating system, none of the hypervisor or any other software that is running on the system can get access to the content which is there in the virtual machine. There are multiple ways of doing this. One way is making sure that the data that is in the virtual machine is encrypted. Nobody can, if somebody tries to access it, they'll get encrypted data, so there's no way they can interpret the data. That is the way I think AMD and Intel does it. We have chosen a different approach here. We'll make sure that neither the hypervisor nor the operating system nor anything else which is running on the system will even be able to access the data or the pages which contain the data. So we are basically fencing the other softwares from accessing the data which is present in the virtual machine. As a result, there is no way data can be lost or compromised. So that's the solution that we have. And the enabling technologies for that is what we call as an Ultravisor. I think this is we call the official name for that is Protected Execution Ultravisor firmware. It's a piece of firmware piece of software that is part of the machine, which gets loaded when you boot up the machine, and that is in control of the machine all the time. And that is that, along with some of the hardware features that are there in the P9 processor, will make sure that neither the hypervisor nor any other thing that is running on the system will be able to access the data which is there in the virtual machine. So we have this piece of software which we call as the Ultravisor firmware, it's in development. And this is the piece that helps us to secure the virtual machine. Now, to understand how this thing works, we need to a little bit understand what are the features in the hardware that helps us enable this technology. We have something called Protection Execution Facility feature in Power 9 processor, which essentially has a lot of features, but the main key components of that of the feature is, one is it lets you segregate the physical memory, like the address space of the physical address space. You have a secure address space and you have a normal address space. Right? All the memory that is sitting behind the secure address space can be accessed only if you have all the privileges. Otherwise, you'll not be able to access it. So we have this secure memory, which is entirely a different physical address space, which is accessible to the software which is running only in a mode which is the secure mode. Right? The secure mode is the piece for here that the CPU provides you a way where only if you have that secure bit on while you are running, you'll be able to access any memory on the system, including the secure memory. If you don't have access, if you don't have that bit on, then you will not be able to access secure memory at all. Right? And there is a mode called Ultravisor mode, which is more of which is more than the hypervisor mode. There's a fourth mode that has been added to the power processor called Ultravisor mode, which is which is more like earlier the hypervisor was the god on the system. Now it is the ultravisor which is the god. The hypervisor has been demoted a little bit. It's kind of an, it has to go through the ultravisor in order to access all the functionalities on all the facilities on the system. So the ultravisor mode, it has access to all the resources, and then the hypervisor mode, which loses some of the access functionality that it had earlier without, if this mode was not enabled, that is protection environment. Sorry, if PEF is not enabled, then hypervisor is the god. But if PEF is enabled, then hypervisor is not, the ultravisor is the god. In the sense, everything has to be permitted by the ultravisor, if you want to access all the resources on the system. And now, if the hypervisor wants to access some of the resources which the ultravisor controls, then the processor provides you a new call, which we call as the ultra call. Apart from system call, hyper call, we have something called an ultra call facility. So you can use the ultra call facility, ask the ultravisor to do the things on your behalf, and the ultravisor will do based on what you're asking for. Right? So that's the functionality in the processor that is supported. And now I'll quickly run through what is a secure virtual machine. We have a secure virtual machine, the image that you have, which is not the normal machine image that you have. You have to change it a little bit. The reason for that is you don't want your image to run on any hardware. You will run the image on only the hardware that you trust. In order for that to happen, you have to put some lock boxes, in the sense some kind of binary bits, digital bits on your image, which provides, which contains the key to decrypt the contents of the image. Right? For example, if you have a normal virtual image over here, we have a tool which will take a couple of inputs. Like if you have a lot of secrets, you can put all the secrets in what we call as the secure box over here, and lock that secure box using the platform keys, the platforms on which you want to run your virtual machine. You encrypt all your secrets using that key, and these are the lock boxes. So for example, if you want to run your virtual image on, let's say, X hardware, Y hardware, and Z hardware, but not on T hardware, then you take the platform keys of those hardwares and encrypt all your secrets which are there over here, encrypt that using that key, and this is the lock box. So that way you create what we call as a secure virtual machine image, SVM image, and this SVM image can then be deployed on the hardware. So when you deploy the image on the hardware, what happens is the image, when you initially start, will be in a normal mode. It will not be in a secure mode to begin with. I think unlike other vendors, the image has to be coordinated by QEMU or something else in order to make it secure. In this case, QEMU need not be changed at all. QEMU remains as it is. The image or the image that is running in the virtual machine, that decides whether it wants to go secure or not. Right? So when it runs, initially it is in a normal mode, but then when it wants to switch to a secure mode, it makes what we call as the secure ultra call. An ultra call that is made by the virtual image, it goes to the ultravisor. Ultravisor does the necessary things like allocating secure pages, moving the data from the hypervisor to the secure memory in the ultravisor, checking the integrity of all the kernels, all the images that you have, before switching, providing that image, the virtual machine image, enabling the secure bit on that image. Before doing that, it does all that integrity check. And finally, if everything works out well, then it gives the secure bit enabled on this image, and then it becomes a secure image. At this point in time, all the pages that the virtual machine had are now backed by secure pages. So because of which, the hypervisor or the QEMU or any other entities that are there in the system, apart from the ultravisor, will not be able to access the content of the secure virtual machine because it is backed by secure pages. So by doing this, we are guarding the virtual machine from any kind of bugs in the hypervisor or a rogue. If there's a rogue hypervisor, it will not be able to access the contents of the virtual image, or any kind of vulnerability will be stopped and that is what provides the security to the virtual image, and that's what this is secure virtual machine image is. Sorry, secure virtual machine is. Any questions? Okay.
Actually, yes.
Okay.
Thanks. So what is the actual attack scenario you're trying to protect against? I mean, you're definitely not protecting against a malicious hypervisor in that case because you're running insecure from the beginning, and I don't see any mechanism that would allow the VM to verify it actually is inside the secure part. So that's the one part. And the other one is what I don't understand is how do you move? Oh, well, that gets loud. How do you move that memory from insecure to secure? Is that a different world? Is it just a tag? So does it get encrypted in memory, or is it a completely different section? If it's a different section, how do we tell the kernel that it can't page anymore?
So, okay, question number one was, I think you had some wrong assumption in your question. Can you repeat your question number one?
Question number one is, what is the attack scenario you're really trying to protect against? Because from at least this slide, maybe you're explaining this later on, if I want to modify the VM at the left point, I can modify the VM, correct?
You can't modify if you modify the VM, then the VM will not be able to move to secure mode because the Ultravisor will check the VM for integrity. If everything is good, then only you'll be able to move it into secure mode.
So what is the downside of not being in secure mode inside that VM?
If it is not in secure mode, then the hypervisor will be able to access the content of the virtual machine, like what is happening here.
So it is encrypted?
It's not encrypted, but it will not be able to access the pages at all. Hypervisor will not be able to access the pages because the pages are now backed by secure pages, and secure pages can be accessed only if you have the S bit on, and that S bit on will be on only if the Ultravisor has provided you that S bit.
Okay, but if I'm malicious, I'm trying to introspect what's inside that VM, I want to modify it, I can just fake the secure piece, I can just fake the ultra call. I don't know. I don't know how the semantics on the architecture work, whether you can do an ultra call from, say, PR mode.
You could make an ultra call, well, you cannot make an ultra call from PR mode, but you can make an ultra call from a supervisor mode.
Right, so what we could do is we could just run the VM in PR KVM, fake all of it. Okay, so I guess Michael can explain that to me then.
You need the
wait.
Well, you should explain.
Okay. So you cannot, let's say you are in supervisor mode and you can make a ultra call. That's what the point you're trying to make, right? Or is in PR mode. In PR mode, I don't think you can make a ultra call. It will fail. In a supervisor mode, you can make an ultra call.
Will it fail or will it trap?
It will fail, I think. It will fail.
Okay, if it fails, then it's fine. If it traps, I could emulate.
Yeah, it will fail. But if in a supervisor mode, if you make an ultra call, then yes, it will come to the Ultravisor. And Ultravisor will look at the image, check for integrity, because we have these lock boxes here. We go check the integrity of the data that is there. And if all the integrity check verifies, then only it will be moved. All the content will be moved into, well, if the content will be moved, verified, and everything checks, then only it will be allowed to continue running by enabling the secure bit on, which means from then onwards, it will be able to access the secure memory.
So what I'm not quite understanding is the usual scenario that people try to protect against with all the secure virtual machine pieces like the AMD implementation and Intel's interesting approach of putting KVM underneath Linux and a couple of other ones are always against protecting against the hypervisor. So you assume all of your hypervisor is malicious.
Correct. We assume we don't trust, well, I don't say malicious, we don't trust the hypervisor. Well, the hypervisor could have bugs. So it may not be malicious, could have bugs, somebody could exploit them and get into the virtual machine. So in any case, we don't trust the hypervisor. In this case, you have to just trust the Ultravisor because only the Ultravisor is the one who can access the content of the virtual machine, the secure virtual machine.
Right, so if I throw resources at it and just say I'm going to JIT my VM at this point, as long as I have the insecure part in the beginning, I can always just fake the fact that it is secure now.
Which part are you talking about? Sorry. Okay. So which part is the insecure? This part is the insecure. Yeah. The QEMU part is the insecure part. Yes.
You're starting off insecure. The VM basically is just running normal execution. It's not encrypted. There's no verification on whether what it's running is correct.
Yeah.
There's no encryption afterwards either. You don't have any decryption step from the Ultravisor, which actually unlocks the guest content based on a public-private key mechanism.
Right.
Which means that if instead of running on bare metal, I just run all of that in emulation, I can just fake the Ultravisor, tell the guest, yeah, sure, you're secure now, and the guest will happily do whatever the guest does, so I don't get any security, really.
Again, how would you fake the Ultravisor? Because
I don't even run PowerPC instructions. I just run that. I mean, I just JIT the whole VM.
Right. So okay, if you emulate it, are you emulating in Ultravisor mode? Or are you emulating in some other mode?
I'm just emulating whatever I like.
Right.
I mean, I can
Which
just
means
call
you cannot emulate in Ultravisor mode. You have to have the Ultravisor bit on, enabled, in order for you to do what you're thinking of doing. Otherwise, you'll not be able to do that. You have to be in that guard mode, which is the Ultravisor mode. Right? If you are trying to emulate the instructions in some other mode, then you will not be able to provide whatever facilities that you're trying to provide to your.
We can take that offline because this is going to spoil the presentation now. But I don't. 5 minutes. Okay, I see. Go ahead. Okay. Please go ahead.
I think I'm on. Yeah, sure. So this is how it. So I'll roughly talk about. I think I talked about how secure virtual machines run, and I've got only 5 minutes left. So I'll quickly introduce what an Ultravisor is. Mostly, I think we have understood it, but go through the individual pieces here. It's a firmware code. It's open source, and it will be GPL soon. That is the first one that gets loaded and gets executed in the secure memory, because it's sitting in a piece of memory which cannot be accessed by anybody else except only the Ultravisor. So its job, the responsibilities are, as I told earlier, it authorizes and validates with all the key mechanisms are there, which goes and validates the contents of the virtual machine before trying to move it into secure mode. It does that. It manages the secure memory. It backs the secure pages to secure virtual machines, moves the data, and also it provides the ucall handlers. Like the hypervisor can request services from the Ultravisor through ucalls. Same case with the virtual machines as well. The other thing is, most of its responsibility is towards managing pages, secure pages. Other responsibilities like scheduling, I/O, those are still offloaded to the hypervisor. And that we do by reflecting the ultra call and seeing first we marshal the data. When you get an ultra call, we marshal it and see whether the parameters are right. If not, we filter them out and then give the content to the hypervisor, and hypervisor does the service for us for the secure virtual machine and returns back. So changes to the hypervisor as such, a hypervisor continues to work, but only thing is now the memory that it is using, its secure memory, which it does, is not in its control. So we use what we call as the QEMU still has to access the content of the secure memory, for example, for migrating the virtual machine, or for hibernation or any of those kinds of things. QEMU will not be able to get the content, but it will get encrypted content if it tries to access it. And that's the mechanism done by the Ultravisor. So we have this module called the UEHMM module, which kind of plugs into the HMM. And it provides a way of accessing the secure memory through the HMM interface. Right? And that is how you can move pages in and out from the Ultravisor into the normal memory. Again, it will be encrypted and decrypted as it moves across. And we have some patches to the hypervisor which have been posted on the mailing list over here, which does the necessary things. How much more time do I have for this? Am I done? OK, I think I'm on the last slide here. Thank you. I have a lot of backup slides. I will post them on the website. And it contains the steps on how we how we switch a virtual machine from normal mode to secure virtual mode. And any questions, I can always be here to answer. Yeah.
Can you go back to the previous slide?
This one?
So how do you handle I/Os basically, like if you do networking or storage?
So to do the I/Os, the hypervisor has to have access to, for example, VirtIO, right, or the virtual private network. In the case of I/O, it is VirtIO. For VirtIO, you are doing the hypervisor needs to access the buffers. For it to access the buffers, it will not be able to access the buffers because it's in secure memory.
Yeah.
So we have to modify or enhance this particular kernel in this virtual machine for it to do bounce buffers. To do bounce buffers, first it has to share some of the pages with the hypervisor. There's some ultra call which you make to the ultravisor. The virtual machine tells the ultravisor, can you please share this particular range with the hypervisor for me? And the ultravisor will go to the hypervisor, get some normal pages, and back normal pages to that range. And then onwards, it will be able to bounce the content from those pages, and the hypervisor will be able to access them. Okay. So that's how we do that.
Also, the encryption, is it software?
Sorry?
When you encrypt and decrypt?
Not for shared pages. If for other things, yes. If any content moves into the hypervisor, it will get encrypted. Any content which is take from the hypervisor into the secure memory, we'll check for the integrity and then only decrypt it and bring it back.
So you mentioned that it is like another set of memory in the system, the secure memory.
Correct.
How can that be resized, or is it really just not a duplicate of the other memory?
No, it is entirely a different memory. It's like GPU memory. If you know of GPU memory, it's like heterogeneous memory, right? It treats this memory as heterogeneous memory. It's a memory which resides entirely different in a different place, and there is this module which helps to bring the pages in and out.
Okay, so for example, if I would plug a new DIMM module in my system, I would only get half of it because the other half is reserved for secure memory?
You can configure it at the time of boot.
Okay.
You can say, I want so much secure memory, and it will set aside that much memory for secure memory,
okay,
secure
thanks.
pages.
Hi. So when you start the VM, do you have to reserve the entire memory that is required for the VM in the secure memory, or can you do on-demand allocation for the pages?
For the normal.
So assuming that your guest has been reserved for like 4 GB of RAM,
okay.
So you need to allocate. Do you allocate 4 GB of RAM in the secure memory, or do you allocate the secure pages as and when you go?
Right. Okay. So you is the one. The Ultravisor is the one who associates pages, and it can do paging on demand. Like whenever the page is needed, it can allocate a new secure page and associate with it. So it can do paging on demand. So whatever the hypervisor does for normal memory, normal pages, the same thing Ultravisor does for secure pages for the secure virtual machine. Does it answer your question?
So back to the integrity check.
Uh-huh.
I mean, it's kind of odd that you boot first the VM into normal mode and then you kind of say, okay, now secure it. How are you going to check the integrity? I mean, what do you check basically?
You want to take that answer? Sorry, go ahead.
So what we actually do is that the VM has what's called an ESM blob, and inside of that ESM blob is a bunch of information, including information allows you to check the integrity of the VM. So what happens is you actually switch to your ESM call embedded in the secure VM is right after prominent. You don't get any further than prominent. What happens is the VM is copied into secure memory at prominent time, and then the Ultravisor has a key that allows it to look into this secure blob, and it has the integrity information for all the components of the VM. It then checks the components of the VM that are still against the integrity information that was created when the VM was created. If the integrity information that was recorded by the tooling when the SVM was created doesn't match what was copied from normal memory into regular memory, then the VM will not execute and it fails. So you can't run the VM for an arbitrary amount of time before it switches, because you're correct. That doesn't work. You can also not emulate that. Ram didn't mention it, but the virtual machine disk is encrypted, and the passphrase for the virtual machine disk is inside of the integrity information by the Ultravisor. And the only way you can get the VM as it proceeds into the boot process can get the passphrase to decrypt its virtual disk is if it uses an ultra call to get the passphrase. And if you're not running in secure mode, that ultra call will not fail. So you will never be able to decrypt the disk, etc. I'm giving a detailed talk on the hardware and stuff tomorrow.
Right. All the cryptographic pieces Guerney is going to touch in the LSS talk, which he has tomorrow.
Okay, I think we have to end now. So, thank you.
Thank you. Thanks, everybody.